Hey everyone, this is Raptor Chatter, and today we're going to be looking at some of the biggest paleontological finds from August 2023. So let's get started. This first paper is actually just a preprint. It's not officially published yet, but it has been accepted to a journal and just needs some relatively minor edits. And it's actually really interesting because it's looking at fossils from before the Cambrian explosion during the Ediacaran period. The fossils come from Nigeria and include a number of different things, including Brigaria, which is likely a holdfast, essentially what would hold the organism to the seafloor while the rest of it actually stretches up into the water column. You can see these in modern-day crinoids and also fossil crinoids. There's also fossils like Parodischia, which is a kind of trace fossil, meaning there is something moving through the seafloor, as well as potential fossils of Botanillaformes. While the fossils are a little bit indistinct here, it is probably a body fossil, which means it's the actual body of the organism that fossilized, not something that was just left there like a holdfast trace or potentially even just some burrows going through the sand. It's something real and tangible about the organism, even if it was a very early and simple organism. This site is really interesting because it's actually closer to the Cambrian than most other Ediacaran sites, and it's also impressive that it does have these holdfast and potential body fossils, because normally that's not really what we get. Instead we get essentially negative impressions of the fossils. You can see my video on Tribrachidium for a little bit more on that and how that organism lived, and also how it was fossilized. So this new site coming from Namibia is really exciting. It's in a protected wildlife reserve, so hopefully the fossils will be there for a long time, and then people can research them in even better detail in the future. As for that brief discussion on fossils having different modes of preservation, that's all under taphonomy. Taphonomy is essentially the study of what happens to an organism after it dies, and that can be anything, from it being scavenged upon to it getting buried by rock and just fossilizing for millions of years. It's a very large field. However, importantly in this case, there was a new look at how certain animals might become so well fossilized. This is particularly true of arthropods, so things with different joints in their limbs. Think spiders, but also crustaceans, insects. You get the gist. In order to try and identify how some really nice fossils of these organisms are made, these researchers actually took some modern-day arthropods, specifically Triops, and put them in mud and left them there and watched how they decayed. And they did this with a number of scans that were able to actually look inside and see the void left by the organism as it decayed. But then they also opened it up and did some dissections to see what parts were left. There's a lot that went into it to try and make sure everything was very well managed, but it does seem like this is a pretty normal process for essentially the animal to decay but still leave that void. This void means that if water is later flowing through the rock, you can potentially get minerals in that water to precipitate out and fill in that void exactly as it is, leading to some of the really great preservation that we do have of certain arthropods. On the subject of great preservation, sometimes soft tissue can be really hard to identify in the fossil record, and that's true of even very well-preserved specimens like many of the Keichousaurus fossils that come from China. They're really, really well-preserved, we can tell a lot of different things about them, but sometimes it's hard to do that. And this includes sometimes needing to use destructive methods to actually sample and see what soft tissue there might be. One of those destructive methods has been the old method of using X-ray fluorescence, or XRF. This generally meant grinding down the fossil very flat, shooting the X-rays at it, and seeing how they bounce off of it to try and see if there's any differences in the rock that might indicate soft tissue. This paper, though, was able to introduce a new method using XRF, which doesn't require the fossil to be nice and flat. It can actually account for the irregularities present in the fossil and the surrounding matrix in order to actually not need that destructive method. So it's really nice for being able to process these things a little bit more safely for the fossils. Keichousaurus lived in the Triassic oceans, but just before that the oceans had a lot of different life that lived during the Paleozoic, and that's especially true of the corals, which were primarily things like rugose corals, which look a lot like modern-day corals, except they lived alone, which is a little bit strange. However, they also developed lines based on the amount of available sunlight they had. And so what this team of researchers did is looked at those lines on a bunch of different coral specimens from one location. And what they were able to determine is that in this region of China where these fossils came from, there would have already been 4 distinct seasons about 310 million years ago. So we know seasons were an important part of evolution of many different organisms. It also suggests that there was a rainy season during the spring or summer, and this is because there's a sudden dip in the amount of sunlight that these organisms would have had access to. So essentially, during the winter, they would have had less, and then they would have been more sunny during the spring, and then towards the end of the spring into the summer, they got rain again, and that blocked out a lot of that sunlight. Then in the fall, those rain clouds cleared up, but of course it was becoming winter, so the days eventually shortened again. It is really interesting to see that we are able to detect exactly when, or at least how far back, seasons might actually go. The rugose coral died out in the Permian-Triassic extinction, and there was a lot of reasons for that, mostly the Siberian traps, which released a lot of volcanic gases and then changed the climate with those associated gases. However, a new study suggests it wasn't just those volcanoes that were important to how life recovered after the Permian-Triassic extinction, because in the early to middle Triassic, there's some volcanoes in China that were also erupting, and they produced very large layers of tuff. TUFF, a type of volcanic rock made by condensed volcanic ash. These kinds of volcanic eruptions probably had a very significant effect on life just about 5 million years after the end of the Permian. So, just 5 million years after that extinction. And that's because even fairly large volcanic eruptions in the modern day can have a significant impact on life, like the year without a summer when Mount Tambora erupted. The ash released by Mount Tambora was enough to block out the sun so much that it snowed in July in the northern hemisphere. So very significant effects were had just because of one eruption. With this series of volcanoes in South China during just again 5 million years after the Permian-Triassic extinction, occasional years with sudden famine brought on by sudden cooling from these eruptions would have been pretty devastating and just another obstacle for life to try and overcome on its path to recovery. But life did recover in the Triassic, and there's some very strange animals that lived during that time, such as the silesaurs, which, depending on what study you're looking at, may or may not have been the first ornithischian dinosaurs. This paper tried to solve some of that by looking at a lot of the new silesaurid occurrences that people have been finding coming out of Brazil and Argentina. Unfortunately, what they found is fairly inconclusive. They might be the first ornithischian dinosaurs, or they might just be the sister group to dinosaurs, so technically not dinosaurs, but very closely related, which is really unfortunate because we'd love to know what these things are. I personally would love to know what these things are because I think they're very interesting, but we just don't have that much data yet because oftentimes these fossils of silesaurs are very broken up, so it's hard to tell exactly what they were. But even as the silesaurs and dinosaurs were evolving, there were still other animals evolving, including some of the top predators of the Triassic, the pseudosuchians, which were crocodile-line archosaurs, closely related to the dinosaurs, but still distinct. And one of them seems to have had some convergence with a later dinosaur, Allosaurus, while also having some pretty distinct differences. Saurosuchus was a top predator during the late Triassic, and its skull seems to have had similar stress points as Allosaurus. However, research now has suggested that it probably also bit a lot softer, which is important when you're considering how it may have fed. Because Allosaurus definitely fed on meat at least close to bones. It wasn't necessarily cracking the bones open the way Tyrannosaurus rex did, but it was feeding on the meat directly attached to the bones. Meanwhile, it seems like because of this weaker bite in Saurosuchus, it would have mostly just been going after the softer meats of whatever it was feeding on, meaning there was potentially a lot of waste involved in what it was eating, meaning that other animals in this ecosystem would have been able to rely on that carcass as a source of carrion. So it probably was a very important part of its ecosystem by providing different carcasses for many scavengers and smaller predators to also feast on. There's also a new proterochampsid found coming from Brazil, and from the Triassic of Brazil. Pinheirochampsa rodriguezi lived in Argentina during the Triassic, and it was a proterochampsid, which is this weird group of crocodile-like archosaurs that we don't really know where to place on the archosaur family tree. Pinheirochampsa really doesn't do a lot to help us better understand what they may have been, but because it's from Argentina, where I already mentioned many silesaurs have been found, it really does help to suggest that South America was a very important site for the evolution of many of these organisms, especially when we look at the number of archosaurs there, because there's a ton of them. So potentially South America is actually holding the key for how dinosaurs, and also many of their relatives, first evolved. Another group which first evolved during the Triassic are the turtles. And for a long time we didn't have a lot of knowledge about how they actually did evolve, but there have been some new fossils that really help to shed some light on that. In this case, we're going to be looking at Odontochelys, which looked like a turtle, except it didn't have quite the entirely hard shell on its top half. The bottom half seems like it was mostly armored, though. But this paper wasn't looking directly at their evolution, but rather their behavior. It used different isotopes that can vary in different parts of the environment to try and understand what Odontochelys would have been eating. And it seems like it would have been a forager on marine plants in shallow water. So it's actually kind of similar to what marine iguanas do today, where they just dive into the water, eat the plants, and come back out on land. This is really interesting because hopefully it's close to the start of the origin of turtles, and we can try and understand how they actually evolved through that. But it wasn't just turtles. There were also things like Prosaurosphargis yingzishanensis, which also comes from China. The saurophagids were this really strange group of turtle-like reptiles that weren't directly related to them. And this is another early one coming from this part of China. Unlike many of the other saurophagids, Prosaurosphargis seems to have actually been pretty large, measuring over 5 feet in total length. Additionally, it's been found in a region where there's 4 other groups of marine reptiles, meaning that potentially, just like South America was for the dinosaurs and their relatives, this region of China with its shallow seas may have been very important for understanding the evolution and origins for how many of these marine reptiles that dominated the later Mesozoic oceans actually started to take their first steps into the ocean. But once those groups evolved, they spread pretty rapidly, and then you had diversification points for other groups. And that includes with a new Dracaeosaur coming from India during the Middle Jurassic. Tharosaurus indicus is this new Dracaeosaur, and that actually makes it part of the larger Diplodocoid group. The Diplodocoids and even the Dracaeosaurs are better known from other continents than India, which was kind of on its own kind of individualized area for large parts of the Mesozoic. However, this is important because it suggests, hey, maybe the Diplodocoids started in this region, essentially on the eastern half of Pangaea, and then migrated everywhere else and became more famous in places like North America with Diplodocus, or potentially even in South America with many of the other Dracaeosaurs like Amargasaurus. It's interesting to think that this group that we know really well from the Americas might have actually started somewhere entirely different. And as for the oceans, there were still things evolving in there during the Jurassic as well, including some fish that had eyes bigger than their stomach. Pachycormus was a fairly widespread fish during the early Jurassic, and there's one from the Posidonia Shale of Germany which appears to have choked on an ammonite. This is interesting because Pachycormus doesn't seem particularly well adapted to actually eating hard, bony things. Instead, it seems like it was mostly eating soft things, including as an adult, it probably ate a lot of squid and things like squid. And ammonites would fall into that category except for their hard shell. So maybe they actually did have a strategy for extracting the ammonite from the shell, and this one just failed to do that and then choked on this large shell from this ammonite. Or potentially it was just mistaken identity and it couldn't see well and grabbed what it thought was a squid and then turned out to be fatal for this fish. Unfortunate for it, but a really neat fossil. Earlier I mentioned the proterochampsids, and now I'm just mentioning a new Champsosaur. Well, not necessarily a new one, but a new specimen of one. Specifically, Champsosaurus lindioi. Until now, this species had only ever been found in Canada, but now there's a new, really fantastic fossil of one coming from the Two Medicine Formation of Montana, which suggests they had a larger and wider distribution than previously thought. It also helps to suggest that, hey, since they were widespread, that may have helped them be one of the few species that actually survived the KPG boundary, when the giant rock came in and hit the planet and lots of things died. This was one group that didn't, and potentially that large range is part of the reason that they did it. Hopefully there will be more future study on this fossil, because again, just look at it, it's beautiful. But until then, this is really all we have. Hey, they had a larger range, and that may have helped them survive. Staying in the Cretaceous, there's also the first fossil of a pterosaur coming from Ukraine, specifically the Burrum Formation. It's a marine formation, and the fossil isn't the most wild and interesting thing around, it's just a tooth. But it does at least help us to know that during Europe, at this time in the Cretaceous, there were still toothed pterosaurs flying around. Meanwhile, in the later Cretaceous, we pretty much lose all of the toothed pterosaurs, and primarily have just beaked pterosaurs. So interesting to see kind of how their distribution was spread out around the world and how over time the toothed type started to lose out to the beaked type of pterosaurs. And still in pterosaurs, there's been some studies suggesting, hey, these pterosaurs would hatch and they were basically the same shape as adults. I mean, they could just take off and fly right away and maybe eat smaller things, but basically be able to take care of themselves right out of the egg. However, that's really only been done for small pterosaurs like Rhamphorhynchus. It hasn't been done for large ones like Pteranodon, for which we have a really good number of specimens and can do those kinds of comparisons. Turns out that they did not grow the same way. Relative to the adults, young Pteranodon actually had much smaller wings to the overall body size. What this means is potentially they actually needed to be cared for by the adults, rather than just kind of let to go free like it seems to be the case with things like Rhamphorhynchus. Still in the Cretaceous, there is a new mammal coming from Alaska, which would have been very cold at the time, and it's small enough of an animal, it wouldn't have been able to migrate during times of cold, especially in the winter where it would have been also dark for large parts of the day. Sikuomys micros is this new animal, and seems like it was a placental mammal, meaning it would have had a placenta and been closer to us than to things like marsupials or even monotremes. So, pretty developed for its time. It also seems like it was so small it wouldn't have been able to even hibernate, which means that during winter it probably lived under the snow in the subnivean zone, which is just the area between the Earth and the snow directly above it. This is really interesting. It helps to show a lot of diversity in what mammals were doing and potentially hint at some of how they were able to survive the big impact by the rock from the sky, because things would have gotten cold, and if they were already adapted to some level for cold, would have made it easier to actually get through that boundary. Staying with mammals, but jumping way up to almost the modern day, we're going to be looking at what happened with the extinction of large mammals in Australia. And how they were able to tell this is by looking at fossils of fungi in ocean sediments. So they cored down into the ocean floor and pulled out what the rocks were and went, oh hey look, there's some fungi here, which mostly come from things that are growing on large animal poops. Unfortunately though, they end up disappearing right about 43,500 years ago. This is right about when humans were showing up on the continent, which makes it seem like they were probably the primary drivers of this extinction. And it could have even just been introduced wildfires that actually helped lead to this extinction, because we also see a die-off of certain types of large plants and fruiting plants, which would have been a very important resource for most of these animals that did die off. Unfortunate for them, again, but that's what life is sometimes. Speaking of fires and extinctions, it seems like something similar happened for the Rancho La Brea fauna. This is the fauna that lived at Rancho La Brea, or the La Brea tar pits. There's a lot of organisms that have been found there, and by timing when different ones actually existed or died out locally, or potentially migrated to other areas, researchers were able to suggest that the change in the general climate and environment of both drying and then large wildfires, probably spread by humans, changed the environment enough that the animals really couldn't do that well. And that's likely what caused many of these different organisms to die out. If you go to the La Brea tar pits, you will see statues of large mammoth and mastodon outside in the tar pits, displaying what may have been happening when some of those animals died. And it's actually really interesting, because those are really, really weird elephantiforms. Even modern day elephants are actually really strange elephantiforms, because most elephants, or fossil elephants at least, had long lower jaws. And sometimes it's hard to know exactly what they were used for. It seems like oftentimes they were actually using it to help process trees. However, during the Miocene, it seems like there was a significant change that actually caused that to no longer be the case. This paper looked at different isotopes from different elephants from the Miocene to try and understand how they may have actually lost this long lower jaw. What they found that was most useful was in Platybelodon, because its isotope suggested it was mostly feeding on things around the water, so things like water grasses. Meanwhile, most other elephants during the same time period were actually feeding on trees. This meant that as the Miocene cooled and grasslands expanded, an animal like Platybelodon was more able to adapt to eating those grasses than the other elephantiforms were. So potentially this drying environment is what led to the kind of short-chinned elephants we have today, as opposed to the very long-chinned one we had in the past. And it's not the only paper suggesting that grasslands are really why elephants are the way they are. There is another one that was looking at their teeth shape and found that, yeah, during the Miocene there is a change in the wear pattern which suggests they were eating more grasses. So it really seems like the start of the ice ages during the Miocene, when the temperature started cooling and grasslands started expanding, is really what led to elephants being the way they are today. And staying in the Miocene, there was also a scan of a fossil seal, Hotamotherium valentoni, had its skull scanned, and from that researchers were able to see where different structures on the brain would have been and how large they may have been. And what they found was an increased size to the coronal gyrus, which is really, really important for trying to figure out where you are in a 3D space. So when you're in the water, for example, that's very, very important. So it seems like this animal would have been one of the first seals to start moving to the water a bit more and start evolving this kind of coronal gyrus that'd be better adapted for life in the water, especially hunting in the water. So really interesting to see this and try and understand how these organisms actually had their brains evolve and not just their direct body plan evolve. And there's still more coming from the Miocene. Specifically for this time, it's actually looking at the climate in India based on new fossils. Lagerstromia piriformis and Milieta sewalica are two plants with living relatives, and these fossils come from just south of the Himalayas. This is important because that's generally a fairly dry region today, but during the Miocene it seems like it would have been very wet and humid, kind of a rainforest type environment. So very different from what we see today in the same place. There's also fossils in North America that have been really useful for biostratigraphy. Biostratigraphy is just the ability to use a fossil to tell what time period you're in. This paper looked at 312 fossil rodents from 124 different locations across North America. And based on the times that different organisms show up, there's 12 distinct time zones that can be told using rodent fossils. So this will be a great tool for many researchers doing work in the Cenozoic of North America. Because if you have one of these organisms, you can go, oh hey, it turns out we're in the Oligocene and not the Eocene, or whatever have you for those fossils. And jumping back in time a little bit further to the Eocene, there was the Eocene thermal maximum, which was caused by the separation of Greenland and Europe, and lots of volcanism, lots of gases released, caused a lot of warming the same way the Permian Triassic did, but not the same die-offs because life was just in a different state at that time. However, this is important for understanding how different environments would have been, including based on some fossils coming from South America. Acmopyle grayi was a conifer tree, and it has living relatives in Fiji and New Caledonia, which, halfway around the world from where it was found in South America, but suggests that at this time in South America, 52 million years ago, that region in South America would have been very, very wet and humid, as, again, opposed to today, where it's Patagonia, it's a grassland and semi-arid plain. It's absolutely not a wet and humid place. So helps to show some of the different climatic changes that were happening during the Eocene thermal maximum. Staying in the Eocene, there was also a very small basilosaurid whale found. And basilosaurs were one group of very early whales that were fairly successful. This one, though, is very, very small. Tutsitus rhadinensis is this new early basilosaurid, and it lived at a time where at least some whales, or at least recently, some whales still would have been at least partially on land, meaning that potentially we can try and study this animal more in the future and get a better idea of why those whales did successfully and the whales that were still at least partially attached to land really didn't, because it's not like seals had evolved at that point. There was still a lot of open niche space for animals living partially on land and partially in the water. And that moves us into papers that I've already done entirely separate videos on, including another basilosaurid, which might actually be the largest animal ever. This is Prucetus, and it's known from a few fossil vertebra that make it seem like it was very, very heavy-bodied. We don't have a ton of it, and there's potential for more fossils of it to be out there at the same locality. They just haven't been pulled out of the ground yet. So hopefully we'll get some more research on these basilosaurids to try and understand why there's such a large size discrepancy between them, and also potentially what they were doing with their lives. There was also a look at some fossils from Rancho La Brea, specifically of Smilodon, to try and see what kind of sounds it might have made. And it turns out that based on the shape of the hyoid bones, it may have actually sounded more like a house cat than like a lion, which is a little bit funny to think about, but also may not entirely be the case, because it actually had some distinct differences from either house cats or lions. The shape again is more like a house cat, but parts of its hyoids were still ligamentous, meaning it wasn't actually bony, there was just ligament holding that. And that is more like the big cats. So potentially it could have still roared like them, but more likely in my opinion is that it was doing some other weird, strange third thing, meaning that it wasn't producing a sound like house cats or other small cats, or like the big cats of today. It was just a strange animal doing its own thing. There's also a look at some snake vertebra, because snakes kind of suck in the fossil record because a lot of their body is really similar between different species. And this paper was able to map out certain traits within snake vertebra and use that to identify some potential snake fossils to what they likely were. And by that I mean essentially, hey, look, we looked at some fairly recent fossils of some snake vertebra and we're able to attach them to modern day species of vipers. So this is going to be things like rattlesnakes, copperheads, and cottonmouths. And jumping back to some of those same Triassic rocks that I had previously talked about in China with marine reptiles, there was a new look at the fossil ichthyosaur Prosaurosphargis. And it turns out it was convergent on some baleen whales, meaning that it was probably filter feeding rather than being an aggressive predator. It was toothless, so that makes sense that it wouldn't have necessarily been going around and eating large prey, but it was also fairly small, meaning that it essentially had a similar skull structure as an animal 10 times its size because it was using it for the same thing, just on a much smaller scale. And then coming from South America and being an archosaur from the Triassic, we have Venadoraptor. Venadoraptor seems like it may kind of be this missing link between the Lagirapitids and the pterosaurs. The Lagirapitids were a group of reptiles very closely related to the pterosaurs, and they had some similarities with things like the shape of their femur, but in this case it's actually more important to look at the hands because you can see that the fourth digit, so what would be the ring finger on us, is enlarged, and the fifth digit isn't there. We already know that a lot of reptiles have actually lost that. However, in this case, that's important because the pterosaurs fly on an enlarged fourth digit. So what it seems like may have been happening is that this was already enlarging as the Lagirapitids were hanging around in trees and things, and then the pterosaurs also just took that to a much larger extreme in order to be able to start gliding between trees and eventually flying on their own. Hey everyone, thanks for watching. You're super cool people. Oh god, I am recording, thank god. I definitely panicked and thought I didn't hit record there for a moment. I'm going to be at Society of Vertebrate Paleontology meeting in October, so, if I see you there, hi. If I don't see you there, I don't see you there. The month in reviews are an important service. They don't do so hot on views, so I really do appreciate the support. If you can financially support us, be sure to check out our Patreon. If you head there, you can check out some of our different votes that we have for the different what the hell videos. So thanks everyone, be safe, take care, don't go extinct.